All right, so this lesson, I'm breaking this into two parts. So we're going to take a look at the definite integrals, just section 4.2. I'm going to call this part 1. So as we finished up section 4.1, I noted at the very end that to figure out the exact area or distance, we would use this limit, kind of like a limit definition of an integral. But it's the limit as n keeps increasing without bound. So if we try to do rectangular approximations, the number of rectangles we're using keeps increasing. And then what we do is we just add all the areas up. So there was a new way to write this. So again, at the end of the lesson, again, pause the video to copy this down. But it turns into the integral. So again, this whole part right here becomes the symbol of the integral. And it's over a closed interval from a to b. And then we just have f of x times dx. So the f of x are the y values. Those are the heights of the rectangle. And then dx is the delta x. It's the width of each rectangle. So that's another way to write this. So we call this the definite integral. We're also going to have something called the indefinite integral. And all that means is we don't have any a's and b's up here. So a definite means we have a definite closed interval that we're evaluating this integral from. So the definition of a definite integral is from, if we're looking at the definite integral from a to b of a function, is this integral notation, the integral from a to b of f of x dx, provided that the limit exists and that f is integrable, like just like differentiable, that we're able to integrate it, take the integral of it on the closed interval from a to b. So we could see different variables here. Notice this very first one I have as the integral from a to b of f of x dx. Or it could be the integral from a to b of f of t dt for dealing with time. Or it could be the integral from a to b, we could say f of r dr. So whatever variable is here, it's going to match here. So if we have a f of t, we'll have dt. If we have f of r, we'll have dr. So those are the different ways we could write this. These are all going to be evaluated the same way. Now, just to get some practice, because on WebAssign, I put a couple questions on there just to help you get used to rewriting this. But again, once we start using the integral notation, we don't go back to the limit definition. So here, let's express the limit as n increases without bound of the summation as I goes from 1 to n of this expression here, and yes, I do have the sub i's, times delta x. We're going to write this as an integral on the interval from 0 to pi. So again, pause the video if you still need time to copy that down. All right, so remember, it's this whole part here, which is just going to turn into the integral. What interval are we on? We're on 0 to pi, so we're going to write this as 0 to pi. And then pretty much we just lose all the little sub i's here. So this is just going to become our function is x to the 4th plus x times cosine x. And then the delta x here simply becomes the dx. And that's all there is to rewriting it. It just forces you to understand what the a to b is. This right here, this is our f of x. And then we have our dx. So this is our f of x up here. We just take out the little sub i's. The little i's here, again, that's because we're going I equals 1 to n, so that's going to be the height of each rectangle we're going to write here. All right, the second example, it's still kind of taking us back a little bit to like the LRAM, RRAM, and MRAM that we did in section 4.1. However, we're not going to graph this. Look at our function. It's f of x is equal to x cubed minus 4x. We're taking the sample points to be the right endpoints, and a is 0, b is 2, and n is 4. So again, pause the video to copy that down. And rather than graphing, we're just going to try to figure this out without graphing. All right, so our interval from a to b, that becomes the 0 to 2. And n is the subinterval, so n equals 4 means we have 4 subintervals, which is going to help us figure out delta x here. So we're going to take this distance from 0 to 2. So delta x is going to be the difference between 2 and 0 divided by 4. So that means every rectangle, this is going to help us find the width of every rectangle that we're going to do here. So 2/4 will just become 1/2. So we have the base of each rectangle is going to be 1/2, or the width of each rectangle. So what we're really looking at here is an R-ram, but again, we're not going to graph this. I'm going to write this as, I'm going to use R for the Riemann sum of 4 subintervals. Now, if you remember, if we had the 1/2 times every value, I could just kind of factor that out. And then in here, I'm going to just write the sum of their heights. So I'm going to go back up here and use f of x is equal to x cubed minus 4x. So I'm going to start, if it's the right endpoints, I'm not going to start at 0, I'm going to start at 1/2. So I need to figure out what is f of 1/2. Then I'm going to figure out what is f of 1. Then I want f of 3/2. And then finally f of 2. All right, so again, we're looking at f of x is equal to x cubed minus 4x. I just brought that down here so I don't have to keep scrolling back up. All right, so here we're going to have 1/2 cubed minus 4 times 1/2. So this is going to give us 1/8 minus 2. Out of the way here. So we can have 1/8 minus 16/8. So we're going to get negative 15/8. So that's what I'm just going to put in up here, negative 15/8. Plus, and I'm going to continue for f of 1. I'm going to change the colors here, though. All right, so next is going to be f of 1, slightly easier calculation. We're going to have 1 cubed minus 4 times 1. So that's 1 minus 4, so that's going to give me a negative 3. So I'm going to write in, we could just say minus a 3 at this point plus a negative 3. So we'll just say minus a 3. Okay, next we want to do f of 3/2. So that's going to become 3/2 cubed minus 4 times 3/2. That's going to give us 27/8 minus actually a 6, so we could say 48/8. And then this will give us a minus 21/8. And I'll explain, if you're wondering why these are coming out negative, I'm going to actually explain this. And then we're going to have f of 2. So this becomes a 2 cubed minus 4 times 2. That's actually going to give us a 0. All right, so again, this is just an approximation here, so I should use this symbol. And again, you could use a calculator for this. But we should be getting, if you want to pause the video to try that on your calculator. Okay, turning everything just into common denominators, I just combined the negative 15/8 minus 21/8, turned the negative 3 over 1 into negative 24/8. This gives us negative 68 or negative 15/2, but ultimately this turns out to be a negative 3.75. Now, we were just looking for to evaluate the Riemann sum, but in terms of area, it doesn't make sense to have a negative area. So let's kind of write this out. If we're getting a negative area, it just means that more area lies below the x-axis than above. So almost like direction, we have, where do we have more of the area showing up? So that's why we're going to get this negative 3.75. I'm not going to call it square units. We were just asked to evaluate a Riemann sum. We weren't asked to find the area. However, with integrals, it shows the difference in area or the net area. So if we were to make a graph of this, I'm just going to make a quick sketch here, but you could graph this on Desmos as well. All right, so the graph kind of looks like this. We're going to go up through -2, come back down through 0, then go back up through 2. So this is also 2. So all from 0 to 2, the area is below. Now, if we had any above, we would just kind of combine the two areas together. But area is going to be negative for the sake of an integral if it's underneath the x-axis. And then if it's above, it's going to turn out to be a positive value. So if we did have any of this, if I took this over to 3 or 4, we would get some shaded regions above. And then, so to be honest, I would get everything that would be negative, which would be the -3.75, and anything above would become a positive number. Then I would combine those, and that's going to show that net area, or the difference in areas. Since all my area was below the x-axis between 0 to 2, that's why we're getting a value. So in a way, we're using area to help us determine the value of the integral. So I'm not going to label this square units. We only do that when I specifically ask for area. All right, so this leads us to a special theorem. There's two parts to this, and we're going to introduce part 2 first. This is called the Fundamental Theorem of Calculus, part 2. So this is kind of like the rules or the steps for us evaluating definite integrals. So if f is continuous on a closed interval from a to b, then the integral from a to b of f of x dx just turns into the antiderivative. Remember that capital F from section 3.9, capital F of b minus capital F of a. So again, where f is any antiderivative of f, or if we took the derivative of capital F, we would get the function that's already there. So we're going to go through and practice a couple of these, and that will wrap up this part 1 of section 4.2. So go ahead and copy this down. We're going to take a look, evaluate the integral from 0 to 2 of x cubed minus 4x dx. All right, so we first start by taking the antiderivative of this expression. So we're going to use the power rule. So that, remember, this is where we add 1 to the exponent. So the antiderivative of x cubed becomes x to the 4th over 4. Same thing here, I'm just going to leave it minus 4 times, we're going to get an x squared over 2. But now I'm going to write, I'm just going to put like a vertical bar here, and I'm only going to write this once, this way, where x is equal to 0 to x is equal to 2. After that, we could just put a 0 and 2. So now, just to kind of clean this up, this becomes a 1/4 x to the 4th. 4 divided by 2 will give us a minus 2x squared. And again, as we go from 0 to 2. Now we substitute the values in. This is that capital F of b minus capital F of a. So I want to substitute the top number in first. So this becomes a 1/4 times 2 to the 4th minus 2 times 2 squared minus, but now when I go to substitute the zeros in, I want to put that part in parentheses because I'm subtracting. So now I'm going to get 1/4 times 0 to the 4th minus 2 times 0 squared. So this whole last part is just going to be a 0. What I'm going to get here is 16 over 4, which is 4. 2 squared is 4 times 2 is 8, and then technically a minus 0, so I'm going to get a negative 4. Now, this is the function we just had on the previous page. When we looked at an approximate, we were at negative 3.75, which is pretty close to that negative 4. But again, we were just looking at an approximation. So half of this class was determining the derivatives. Now the rest of this will be looking at integrals. All right, let's take a look at this next example. I want you guys to go ahead and try this. Pause the video to do so. All right, so again, if we go to take the antiderivative of each term, the antiderivative of x squared becomes an x cubed over 3 minus, we're going to have a 2, and then we'll get an x squared over 2. Now, if you could tell where that's going to lead to ahead of time, you can skip that step. Then we're going to get a plus 6x, And again, it's going to be from 1 to 5, x equals 1 to x equals 5. I'm going to clean this up a little bit before I substitute. So we're going to get an x cubed over 3. The 2's are going to divide out, so just minus an x squared plus 6x, again from 1 to 5. I want to start by substituting in the 5. 5 cubed is 125 over 3. Minus 5 squared is 25. Plus 6 times 5 is plus 30. We have to be careful as we subtract. Now, we don't have a 0 here, so I need to definitely keep this in parentheses. I'm going to get a 1/3. Minus 1 squared is 1, and then plus 6 times 1, which is 6. Now, especially in this step, we need to watch our signs. I'm going to go ahead and combine the negative 25 with the 30. So that's going to give me a positive 5. Next, I'm going to have minus a 1/3. In here, I'll have a 5 plus 5. So now I get 125/3 plus 5 minus a 1/3 minus a 5. So the 5's are going to cancel. 125/3 minus a 1/3 is going to give me 124/3. And we could leave it just like that. It doesn't simplify. Let's just try a couple more. Again, if you wish to try this on your own, pause the video. All right, as I go to take the antiderivative of 3x squared, this is going to become a 3x cubed over 3. We'll just have plus a 4x, again from 0 to 3. Now the 3's are going to cross out here, so we're just going to get an x cubed plus 4x. Nice and easy for this one. So I'm going to substitute the 3 in. 3 cubed is 27, plus 4 times 3 is 12. I still want to show that I'm substituting in the zeros, because we never want to just take any steps for granted in case we end up missing something. But 0 cubed is 0. 4 times 0 is 0, so technically I could ignore that. And I end up getting a 39. One more example here. Go ahead and pause it. See what you come up with. All right, so looking at the antiderivative of 5x squared, we're going to get a 5x cubed over 3 minus an x squared over 2. So we go from negative 3 to 0. This doesn't simplify any nicer. However, one of the numbers we are working with is a 0, but that's going to go first. So I'm really going to have 5 times 0 cubed over 3 minus 0 squared over 2. We have to be careful with this next part. We want to subtract. We're going to get 5 times negative 3 squared. So that's going to become 5 times a negative 27 over 3 minus a negative 3 squared over 2. So be very careful here. So these zeros are gone. We're going to have the opposite of, now if this helps, 3 goes into negative 27, so this will just become a negative 9. So we're really just going to get a negative 45. Then we're going to get plus 9 halves, because this will give us, I'm sorry, just minus rather. This will give us a positive 9, so it's going to stay a minus. Minus 9 halves. So if you wanted to multiply this by 2, we're actually going to get a negative 90 halves minus 9 halves. So that's going to give us a negative 99 over 2 on the inside. Then we simply take the opposite of this, so we'll get positive 99 halves as the value of this integral. All right, so we're going to stop there for this lesson. We're still not done with this, so starting next week, I will finish up this part, and then we'll move on to at least another section or section and a half. Please let me know if you guys have any questions.